In this tutorial, we'll cover how to use linear regression using RapidMiner. The discussion is based on the textbook Data Mining for the Masses, Chapter 8. In this textbook, the objective is to predict the amount of heating oil which a company needs to purchase for their clients. So there are two files associated with this chapter. The first file is used to train a model, and the second file is used to make predictions and apply the model and eventually come up with the total amount of needed heating oil. Those chapters are the data sets for these exercises come with the textbook. The training data set comes originally from chapter 4, which we used before. Here is a quick recap of the data set. Heating oil is the dependent variable which has to be predicted by 5 independent variables, and those independent variables are insulation, temperature for the geographic region, number of occupants in the house, average age of the occupants in the house, and home size. Some of those values are absolute, like temperature. Other are relative, like insulation, ranging from 1 to 10 based on a scale. This is an important step because the dependent variable, when the data is being imported, must be labeled as label. So when an attribute's role, the role of an attribute is changed from an attribute to label, it tells RapidMiner that this becomes the dependent variable. I'm gonna call this file oil training. The data was imported. We have 1200 examples, and we can see that the heating oil has turned into a different color because it's become labeled data, meaning it becomes the dependent variable. We start building the linear regression model. After the data has been connected, we want to use the linear regression model operator. The input for linear regression is a training data set, and the output is a model, probably the most important output. When we run the process, we see the model. So we see all independent variables: insulation, temperature, average age, and home size. All of them are significant. This can be seen from the small p-values and fairly large t-values, t-statistics. All of them are above 2 and below -2. However, we still do not see the f-test or the ANOVA test typically associated with the regression, nor r-square. To see some of those performance statistics, actually we need to apply the model, and there is a separate operator called apply model, which requires us input any model and data which will be used to apply the model. In this particular case, we'll use the same data which was used to calculate the model to apply the model on the same data, and then the output, an important output, is a new labeled data set, where in addition to the labeled variable or the dependent variable, we see also how the same variable was predicted by the model. When we run the process, now we see that there are two specific variables. The first one is heating oil, and the second one is how the same amount of heating oil was predicted by our linear regression. So this is what applying a model means. It actually predicts. We still do not have anything to evaluate the performance of the model, and to do so we attach a final operator called performance for a regression. Its output is label data, meaning including something that is predicted along with the dependent variable, and one of the outputs is performance. Now, performance, there are a variety of performance operator numbers which can be seen on the parameters, pardon me, which can be seen on the right side. The one by default is root mean squared error. Actually, we don't need it. It's very useful to compare the performance of different models, but for linear regression, people typically are more used to R square. And R square simply is the squared correlation between the dependent variable, the original dependent variable, and the predicted variable by the model. So we will take the squared correlation of that. And now when we run the model, we see that the R square is almost 82%, which is great. So those three operators constitute what typically is considered linear regression analysis. Although we see three boxes here, the decomposed approach is quite useful, because now if we want to, we easily can change the model to something else and still follow the same logic. For example, let's say I want to use a different model like neural network, which are handy because they can predict anything. I quickly substitute the model with neural network model. I turn off the linear regression operator for a moment, and now use the same setup. We run the model, we see that the R square actually for a neural network jumps to almost 95%, which is exceptional. So the modular approach in data mining is quite handy. Let me I'm connecting back the linear regression model, and now we have the original setup. Something that is important in data mining is to consider how we apply the model. In this case, we apply the model using the same data on which the model was trained. Some data miners may become a little suspicious of that and say we need to apply the model on different data set to make sure it actually predicts as expected. And we can split the original data set into halves, use one half to train the model and the second half to actually predict, to evaluate the performance of the model. To split the original data set in two partitions, we use the operator called split data. Split data does exactly what it says. It splits the data into a variety of partitions. And in our case, I would request two partitions of a relatively equal size, 50 and 50%. We can add as many partitions as we need, and we'll need those partitions here as outputs on the split operator. But for the moment, I need only two partitions. So the first half of the sample now goes to train the model, and we can take the second half of the sample to evaluate the model. So now the first half is used to train the linear regression model. The second half is actually used to apply the linear regression and see how it performs. The new R square is slightly lower, it's 80%, but still quite high, so the linear regression model is very useful. If you want to see the performances simultaneously and apply the model over the original data set and the new data set, the original data set and the second half, the second partition, we can build two performance paths actually. So let's take apply model. Okay, see what happens here. When we attempt to connect or to split a model or data set to multiple operators, there was a quick blink here that suggests a splitting operator, which is typically called the multiply operator. Like, for example, you're gonna see it again. And if you click it, it automatically inserts a multiply operator which pretty much copies the output in a variety of ways. It serves like a fork. So the apply operator is used to pretty much copy the model. Now the same copy of the model is fed to this apply operator, and then the same copy is fed to the other apply operator. I'm going to use performance again for regression. Okay, and now we have two performance paths. So what happens here? First, the data is split into two halves. The first half is used to train a model. Then this model is evaluated over the same data set, but then the model is evaluated again, applying it again over the second half of the data set. So when we run the process now, we are going to see two performances, and they are going to be 82 and 80.8009. Okay, here is, oops, I forgot to click. I'm sorry, let me go back. Here we still go with the root mean square, and for easy readability, let me change the name of those performance operator to performs training, and here to performance scoring for easy readability in the output. So performance scoring here, we have 80%, and performance for training is what we had as 83%. This can be useful also in other ways. For example, because I have two performance paths, I can quickly insert the neural network operator. So now what happens, we split the model in two halves, two partitions. The first partition is used to build a linear regression model. The second partition is used to test a neural network model. So this is not training anymore. We can call this linear regression, and this we're gonna call neural. So now the model is split in two halves, and each half is used to test different models. When you run the process, we see that for neural the R square is 95, and for using linear regression is 83. However, this wasn't the objective of the chapter. These were some variations. The objective of the chapter was to use a new data of 42,000 customers and predict how much oil those new 42,000 customers will need, so that the company knows how much oil to purchase. The new data set needs to be imported. It comes again together with the book, and its name is chapter 8. So what we see here now are only the dependent variables. There is no the independent variables. There is no dependent variable. The dependent variable has to be predicted. All of the attributes are regular because they're independent variables. Let's give it a name, oil scoring. And all scoring will be imported. Let me switch back. I just wanted to show you that the oil scoring has 42,650 customers. So we need to predict how much oil each one of those customers will use, and then sum up their amounts and give this number to the company. This is the business problem. We have a model, the linear regression model. We just connect it and see what happens here. Actually, we can no longer apply the performance operator, because the performance operator needs the original variable and the predicted variable, but the data set which we use to predict doesn't have an original variable, so actually there is nothing to be evaluated. we can delete, actually we should delete the performance operator. And if we run the model in its the process in its current form, the output is going to be the predicted heating oil for all of these 42,650 new customers. The next step is to calculate the total amount of needed heating oil. It's done by using the aggregate operator. And the aggregate operator aggregates or sums up in variety of ways any of the variables we need. So we tell the aggregate operator that for the predicted heating oil we want to see its total amount, and let's add one more. For the predicted heating oil we want to see the average consumption per household. So we're going to see two numbers, aggregate numbers, when we run the process, and those numbers are the total amount of heating oil which the company needs to purchase for the new 42,650,000 customers, and we also see that on average each customer uses about 200 units of heating oil. And this is how linear regression is used.